In this lesson, we will continue our study of power series. We will mostly focus on finding intervals of convergence rather than just radii of convergence. We will also discuss how one can integrate and differentiate power series and what consequences this has for the radius and interval of convergence. So find the radius of convergence and the interval of convergence for this series. So once again, let's just start by applying the ratio test. So first we input n plus 1, so we'll have negative 1 to the n plus 1, multiplied by x minus 3 to the n plus 1, over 2 times n plus 1 plus 1, then multiplied by 2n plus 1 over times negative 1 to the n over x minus 3 to the n. Alright, the negative ones we can absolute value, they become 1, they're gone. X minus 3 to the n plus 1 is x minus 3 to the n multiplied by x minus 3. And also in the numerator we have this 2n plus 1. In the denominator we have a factor of 2n plus 3 and x minus 3 to the n. Now we cancel some things and we have the limit as n goes to infinity, absolute value of x minus 3 multiplied by 2n plus 1 over 2n plus 3. The x minus 3 is a constant. The limit of this expression is 1. So the value of my limit is simply x minus 3 absolute valued, which for convergence that value must be less than 1. So this tells us that the radius of convergence r is equal to 1. Next, let's find the interval of convergence. So because the absolute value of x minus 3 must be less than 1, this implies that negative 1 is less than x minus 3, which is less than 1, which implies that positive 2 is less than x, which is less than 4. So we have to test x equals 2 and x equals 4. So if we input x equals 2 into the series, we have the sum from n equals 0 to infinity, negative 1 to the n, well, another negative 1 to the n, over 2n plus 1. This is the same thing as the sum from n equals 0 to infinity of 1 over 2n plus 1. And you can tell that this diverges probably by the limit comparison test with the divergence series 1 over n. Now let's test x equals 4. In that case we get the sum from n equals 1 to infinity, negative 1 to the n. 4 minus 3 is 1, 1 to the n is just 1, so negative 1 to the n over 2n plus 1. This will converge by the alternating series test. So in that means that for this particular problem, my interval of convergence, which I'll just abbreviate IOC, that is either 2 is less than x, which is less than or equal to 4, or you could write it as 2 to 4 with a bracket around 4 and a parenthesis around 2. Those are two equivalent ways to say that x is between 2 and 4, not including 2, but including 4. Alright, let's do another one of them. Find the radius of convergence and the interval of convergence for this series. So first, apply the ratio test. So we'll have n plus 1, x plus 1 to the n plus 1 over 4 to the n plus 1, multiplied by 4 to the n over n times x plus 1 to the n. Alright, we'll have n plus 1 multiplied by x plus 1 to the n and a singular x plus 1, 4 to the n, all over 4 to the n times 4, n, and x plus 1 to the n. Now let's cancel out common terms. So the x plus 1 to the n's cancel, the 4 to the n's cancel, and we're left with the limit as n goes to infinity of the absolute value of x plus 1 over 4 multiplied by n plus 1 over n. And as n goes to infinity, the limit of this expression is going to be 1. So this limit will just equal the absolute value of x plus 1 over 4. And for convergence, this must be less than 1. And that implies that the absolute value of x plus 1 must be less than 4. So my radius of a convergence r is 4. So next, let's find the interval of convergence. So if x plus 1 absolute value is less than 4, this means that negative 4 is less than x plus 1, which is less than 4. Or negative 5 is less than x, which is less than 3. So now we must test x equals negative 5 and x equals 3. So with x equals negative 5, I get the sum from n equals 0 to infinity, n over 4 to the n multiplied by negative 4 to the n. Now that's the same thing as the sum from n equals 0 to infinity, negative 1 to the n times n, which is definitely going to diverge by the test for divergence. And at x equals 3, we get the sum from n equals 0 to infinity, n over 4 to the n multiplied by 4 to the n, which is just the sum from n equals 0 to infinity of n. So we're adding up 1 plus 2 plus 3 plus 4. This is going to diverge by the test for divergence. So in this case, my interval of convergence is just equal to this, which in interval notation is negative 5 to 3 with parentheses on both ends. Find the radius of convergence and the interval of convergence for this particular series. So once again, let's start by applying the ratio test. So we'll find the limit as n goes to infinity of negative 1 to the n plus 1, x to the 2 times n plus 1 over 2 times n plus 1 multiplied by 2n plus 1 over negative 1 to the n, x to the 2n plus 1. So that's the same thing as the limit as n goes to infinity. That would be x to the 2n plus 3, so x to the 2n times x cubed multiplied by 2n plus 1 divided by 2n plus 3 times x to the 2n times x. And now we can cancel the x to the 2 n's, and we'll have and one of the x's from the x cubed can cancel, so we'll have x squared absolute valued multiplied by 2n plus 1 over 2n plus 3. And this limit, since the limit as n goes to infinity of 2n plus 1 over 2n plus 3 is 1, this limit will be x squared, and we'll have convergence if this is less than 1. And so that implies that x is in between negative 1 and 1. So my radius of convergence r is equal to 1. And next, let's test our endpoint. So let's test x equals negative 1. When I input negative 1, I get the sum from n equals 0 to infinity, negative 1 to the n, negative 1 to the 2n plus 1 over 2n plus 1. And I have to determine if this series really is alternating, because if it's alternating, then we're going to have a convergent series, but if, say, the numerators are always 1, then we're going to have a divergent series. Let's look and see if these terms end up alternating. So when we input 0, negative 1 to the 0 is 1, and the second term will be negative 1 to the first, which is negative. So my first term is negative. When I input 1, negative 1 to the first is negative, multiplied by another negative, making a positive. If I input 2, negative 1 squared is positive. Second term is negative. So it appears to be alternates. But check one more. Check 3. Negative 1 cubed would be negative. The second negative 1 would be negative 1 to the 7th, which would also be negative, giving you a positive. So this will converge by the AST. And x equals 1 is a lot easier, actually. So when you input x equals 1, 1 to the 2n plus 1 is just 1. And we have the sum from n equals 0 to infinity, negative 1 to the n over 2n plus 1, which also converge by the AST. So in this case, my interval of convergence is negative 1 to 1 inclusive. Next, find the radius of convergence and interval of convergence for this particular series. So let's apply the ratio test again. So negative 1 to the n plus 1, n plus 1 factorial, x to the n plus 1, all over 2 times n plus 1 factorial, multiplied by 2n factorial over negative 1 to the n factorial, x to the n. Alright, the negative 1s can just drop out. So n plus 1 factorial will be n plus 1 multiplied by n factorial. X to the n plus 1 is x to the n times x. And then we have 2n factorial. Now, this 2n plus 1 really is 2n plus 2 factorial. So we'll have 2n plus 2, 2n plus 1, and then 2n factorial, multiplied by n factorial and x to the n. Now a whole bunch of stuff should cancel with the limit as n goes to infinity. So the n plus 1 in the numerator stays, the x stays, but the x to the n and the 2n factorial cancel. In the denominator we have 2n plus 2 multiplied by 2n plus 1. So this will equal absolute value of x times the limit as n goes to infinity of n plus 1 all over 4n squared plus 6n plus 2. And that limit is going to be 0. So we'll have absolute value of x times 0, which is 0, which is less than 1 no matter what x is. So in this case, the radius of convergence r is equal to infinity, and the interval of convergence is minus infinity to infinity. Find the radius of convergence and the interval of convergence for this series. Now you could apply the ratio test, but because both the numerator and denominator are raised to the nth power, I'm actually going to use the root test for this particular example. So we'll find the limit as n goes to infinity, the nth root of the absolute value of x minus 2 to the n over n to the n, which will equal the limit as n goes to infinity, the absolute value of x minus 2 just over n. And this limit is going to be 0, which is less than 1. So thus, in this case, we have the radius of convergence is infinite, and the interval of convergence is minus infinity to infinity. If your series only involves terms to the nth power, you can use the root test, but if you have things where you have factorials and stuff, the root test will not work very well. The final topic we're going to discuss with power series are how to differentiate and integrate them. So if you have a function that is defined by a power series, it has a radius of convergence that's r bigger than 0, so not just conversion at c. Then on the interval between c minus r and c plus r, f is differentiable and thus continuous. And here are the derivatives and antiderivatives. So the derivative is going to be a1 plus 2a2 times x minus c, which is actually pretty easy. Look at the expanded formula here. So the derivative of a naught, a sub 0, is going to be 0, it's a constant. The derivative of a1 times x minus c will just be a1. The the next term, the 2 will pull down, so we'll have 2a2, x minus c to the first, etc. So that formula becomes a sum now from n equals 1 instead of 0 to infinity, n times the a sub n's, x minus c to the n minus first. Now if we antidifferentiate, we have our constant c, and then really you would say a naught x, but a naught x is, you can make this into a naught times x minus c, because the a naught times c is part of the arbitrary constant. You can compensate with that constant c. And then the antiderivative of a2 or a1 times x minus c would be a1 x minus c squared over 2, a2 x minus c cubed over 3, etc., giving us this formula. Now, the interesting thing here is that the radius of convergence is the same when you differentiate or integrate. The only difference might be at the endpoints. So we're going to use this to determine the interval of convergence for following series. So first, let's find the interval of convergence for this particular function. And because we have x and 5 both raised to the nth power, let's apply the root test. It will be a little bit simpler. So we'll find the limit as n goes to infinity, nth root absolute value, x over 5 to the n, which will equal the limit as n goes to infinity, just the absolute value of x over 5. That must be less than 1, and that will imply that the absolute value of x is less than 5, or that negative 5 is less than x, which is less than 5. And at x equals negative 5, we get the sum from n equals 0 to infinity, negative 1 to the n, which diverges. And at x equals 5, we get the sum from n equals 0 to infinity, 1 to the n, which also diverges. So here is the interval of convergence for this particular series is negative 5 to 5. And the radius of convergence is 5. Now next let's find the interval of convergence for the derivative of this function. So using our derivative formulas, the derivative will equal a sum from n equals 1 to infinity. You can think about this original series as the sum from n equals 0 to infinity, 1 over 5 to the n times x to the n. So we'll have that 1 over 5 to the n, that's a constant. The derivative of x to the n will be n x to the n minus 1. So this series is a sum from n equals 1 to infinity, n x to the power of n minus 1 over 5 to the n. So we still know that the radius of convergence is still 5 with a center of 0. So we have to test, so we know that x is in between negative 5 and 5. We don't have to do any ratio test because we did the ratio test in the original series. So now all we have to do is test negative 5 and 5 in this new formula. So if we say plug in x equals negative 5, we get the sum from n equals 1 to infinity, n negative 5 to the n minus 1 over 5 to the n, and that's the same thing as the sum from n equals 1 to infinity, well, negative 1 to the n, 5 to the n, 5 to the negative 1, and then that n, all over 5 to the n, which will be a sum from n equals 1 to infinity, negative 1 to the n multiplied by n. That will diverge. Actually, there would have been an over 5 there, but still going to diverge. And when we plug in x equals 5, we have a sum from n equals 1 to infinity, n 5 to the n minus 1 power over 5 to the n, which will equal a sum from n equals 1 to infinity, n over 5, which will still diverge. So my interval of convergence here is -5 to 5. Let's do one more example where we do a few derivatives and an integral. So given this function f of x, find the interval of convergence for the original function. So we'll find the limit as n goes to infinity of -1 to the, well, n plus 2, x minus 2 to the n plus 1, all over n plus 1, multiplied by n over -1 to the n plus 1, x minus 2 to the n. So that will be the limit as n goes to infinity, x minus 2 to the n, x minus 2, multiplied by n over n plus 1, and x minus 2 to the n. And this will equal the absolute value of x minus 2 multiplied by the limit as n goes to infinity of n over n plus 1, which is just x minus 2 absolute valued. So that must be less than 1, which implies that -1 is less than x minus 2, which is less than 1, which then implies that 1 is less than x, which is less than 3. So now we just need to test x equals 1 and x equals 3. So if we test x equals 1, we end up with a sum from n equals 1 to infinity, -1 to the n plus 1, multiplied by -1 to the n, all over n. And the numerators are going to alternate when you plug in n. It appears that the numerator in this expression will always be -1. When you start by plugging in a 1, you'll have -1 to the second times -1 to the first, giving the first term to be -1 over n. The second term, if you plug in 2, the first term has -1 cubed, second one -1 squared, so it'll still be -1. So this is actually equal to the sum from n equals 1 to infinity of -1 over n, which actually diverges. And then when you plug in x equals 3, we have the sum from n equals 1 to infinity, -1 to the n plus 1, all over n, and this converges by the AST. So in this case, my interval of convergence is not including 1, but includes 3. Next, let's consider the derivative. So the formula for the derivative will be given by sum from n equals 1 to infinity, -1 to the n plus 1, n, x minus 2 to the n minus 1, all over n, which is the same thing as the sum from n equals 1 to infinity, -1 to the n plus 1, x minus 2 to the n minus 1. So we are still going to have a radius of convergence equal to 1. We still have the preliminary interval of x is in between 1 and 3. We still have to now check x equals 1 and x equals 3 in this expression. So if x is equal to 1, we get a sum from n equals 1 to infinity, -1 to the n plus 1, multiplied by -1 to the n minus 1. Anywho, this diverges by the test for divergence. The limit of the terms does not go to 0. If you input x equals 3, that implies that we have a sum from n equals 1 to infinity, -1 to the n plus 1, multiplied by 1 to the n minus 1, which also diverges. So in this case, the interval of convergence is 1 to 3, and neither endpoint is included. Next, let's find the second derivative. So in this case, we'll have a sum from n equals 2 to infinity. The first and second terms would both be gone. -1 to the n plus 1, multiplied by n minus 1, and x minus 2 is now to the power of n minus 2. And once again, we still have r equals 1. We have our preliminary interval of 1 is less than x, which is less than 3. We just need to test x equals 1 and x equals 3. So if you input 1 into this series for x, that gives us the sum from n equals 2 to infinity, negative 1 to the n plus 1, n minus 1, and then negative 1 to the n minus 2. That will diverge because the terms are not going to go to 0. And when you input n equals 3, x equals 3, you have a sum from n equals 2 to infinity, negative 1 to the n plus 1 multiplied by n minus 1, which will also diverge as the limit of the terms does not go to 0. So in this one, the interval of convergence is the same as the first derivative. It's from 1 to 3. And lastly, let's find the interval of convergence for the antiderivative of this function. So the antiderivative of this function will be some constant c plus the sum from n equals 0 to infinity, negative 1 to the n plus 1. So that will be now x minus 2 is now raised to the n plus first power over n times n plus 1. And the constant c isn't really important for determining convergence or divergence. We can just consider this part of the series when we're doing that. And I think actually the series has to still begin at 1 because that denominator is 0, so n equals 1. So now when we test, so same thing, we still have r equals to 1, we still have the preliminary interval at x is in between 1 and 3. So let's test x equals 1. So we'll give us the sum from n equals 1 to infinity, negative 1 to the n plus 1, multiplied by negative 1 to the n plus 1, over n times n plus 1. So that will be the sum from n equals 1 to infinity, 1 over n squared plus n, which we know will converge probably by a limit comparison test or a direct comparison test. And if we test x equals 3, that gives us the sum from n equals 1 to infinity, negative 1 to the n plus 1. 1 to the n plus 1 is just 1, all over n times n plus 1, and this will converge by the alternating series test. So in this particular example, the interval of convergence is 1, 2, 3 with the endpoints included.